In this session, we will study about the definition of clocked synchronous sequential networks, the types of clocked synchronous sequential networks, and how to analyze the given clocked synchronous sequential networks. So let us understand the purpose and use of this study. One of the example for a synchronous sequential network is serial adder. Let's take a serial adder. So serial adder can be represented with two inputs. The two inputs not applied parallelly. The two inputs are applied serially if the number width of each of the input is 32-bit. So the 32-bit will be fed in the binary fashion. So both the numbers will be fed in the binary fashion. So since serial adder is a synchronous sequential network and it's a clocked, it requires a clock to work and complete the operation. Every clock cycle, it takes one bit from the two inputs and produce one output. So the outputs is also produced in the serial order. What is an advantage? When we want to build a large size adders and the time is not critical, it's always easy to build using synchronous sequential circuits like this, where after no number of clock cycle, let's say 32, 64 clock cycle, it can add two numbers of size 32-bit, 64-bit. So here the circuit will be very simple. Only thing is time will be multiple clock cycles will be required. So if that is a requirement, how to design such circuits? Let's take another example. So we are building a digital system, again which is based on the clock, and we have to identify in the stream of serial input which is derived from other digital machine or other industrial output. The sequence will be binary data. I want to identify in this binary input sequence 110 pattern. So whenever 110 pattern is identifying the binary sequence, I have to generate some output signal indicating that that pattern is identified in the input sequence. So there are multiple such applications where we require multiple clock cycles and we receive the series of inputs. We perform certain operation on that series of inputs and we'll produce certain outputs. So such examples will force us to learn to understand and design synchronous sequential networks. The general block diagram of a synchronous sequential networks is shown in the figure here. In this figure, so following points are being noted here. In normal counters, we have only flip-flops and outputs of the flip-flops will be used as the output of the circuit, and the clock was inherent and the counters were going from one state to another state. Here two things are introduced. One, inputs which was not there in the part of a counter study is there now, and also apart from the outputs from the flip-flops, we are also producing external outputs. So any clock synchronous sequential network in general not only will have the memory component, that is a set of flip-flops, it also has certain inputs. Generally the inputs will receive in the form of bit stream, and we also produce a bit stream as an output. So all our work with reference to the clock input. Now, so here we mark the two things, present state and the next state. So all these circuits have three characteristics. There is only one single master clock is used, and since it's a single master clock is used, network synchronization is possible and it prevents a lot of timing errors. All the flip-flops what is used here should be pulse triggered or edge triggered flip-flops. It's compulsorily because these flip-flops should obtain their outputs only one time during the clock cycle. So only edge triggered or pulse triggered flip-flops will have that property. That means output change only for a particular transition of the clock cycle. The applied inputs and the present state, will drive the flip-flop inputs to realize the next state. And also the applied inputs and the present state will be used to generate the output logic. So the combination logic is used. This logic decides what is the next state and what will be the outputs. The present state of the network is the current content of the flip-flops that comprise the memory portion of the network. The next state corresponds to the updated information about the past history of inputs that must be preserved by the system. So all the clock synchronous sequential networks will be of two types. So they will be called as two types of models. So one is Mealy model of clock synchronous sequential network. The second is called Moore model of clock synchronous sequential network. The previous diagram is written in this format. So here all the components is there. So memory portion is there. Input to the memory is called as next state. That means that excitation signals. So which is going to drive the next state of the flip-flop. The memory output is called as the present state. The present state and the inputs are used with the help of combination logic, which drives the next state and also which drives the output. In case of Mealy model, the outputs and the next state depends upon both the inputs and the present state. So let's look at the equation. Q plus, that is the next state, is a function of both the present state, which is nothing but Q, and also which depends on the input. Similarly, if you look at the outputs also depends upon the present state, that is the Q outputs from the flip-flops, and also the inputs given to the system. So it's a function of this one. So Moore model is similar to the Mealy model, except that the outputs depend only on the present state. Output do not depend upon the inputs. So let's understand and analyze the given synchronous sequential networks and observe the outputs with reference to the inputs. So let's take one circuit diagram and see the analysis of the clocked synchronous sequential network. So this is a clocked synchronous sequential network. So here two flip-flops are used. They are of the type called D flip-flops. And this is the combination logic. This combination logic takes the present outputs and also the present inputs and drives the excitation inputs, that is in the sense the D inputs of the flip-flops, and decides what will be the next state. At the same time, the present outputs of the flip-flops and the inputs are used to generate the output. Now let's analyze the working of this circuit. So this analysis requires 6 steps, or 6 basic steps are required to analyze this circuit. Now, so we'll do one by one. What is the first step required when we want to analyze the given synchronous sequential networks? So the first parameter required we have to assign, the first step in analysis is assign state variables and excitation inputs to flip-flops. Now, so let's look at the circuit now. So this has got 2 flip-flops, and the output of the first flip-flop let's call as a Q1 and Q2. Q1 and Q1 bar. Output of the second flip-flop let's call as a Q2 and a Q2 bar. So state variables means it's nothing but outputs of the flip-flops. So Q1 and Q1 bar, this is for the flip-flop 1. This is the first one we have to assign. Next, for the flip-flop 2, it is Q2 and Q2 bar is assigned. So now, what is the excitation inputs? We know that when we use the flip-flops, the data inputs to the flip-flop like a D, T, JK, they are called as excitation inputs. Now since two flip-flops are there, so let's call the D1 as the excitation input for the first flip-flop, D2 for the second flip-flop. So it's a flip-flop 1 and the flip-flop 2. Now we have finished the first step in the analysis of synchronous sequential networks. Now let's go to the second step. Derive the excitation equations. Derive the excitation equations. Now, so we know that the excitation variables are D1 and D2. So which depends upon the present state outputs and also the inputs. Now looking at the circuit, we have to write down now D1, D2, this is the excitation equations, and we have to also write output equation. Output equation. So output equation in the sense there is only one output is there, so we call it a Z. Now, so these are the algebraic expressions which defines how D1 will be generated, how D2 will be generated, and how Z will be generated. Now let's look at this diagram and analyze how D1 will be derived. So if you look at this circuit diagram, so D1, so if you look at this, the D1 depends upon OR gate which has got 2 inputs, and one input is provided by the AND gate, so which has got the 2 inputs. One is X bar, other is a Q2 bar. So the second, this is a Q2 bar, so that I can just say that, so X1 bar dot Q2 bar is one of the input, the second input. The second input is taken from an AND gate, where one of the input is derived from Q1 bar, other input is derived from Q2. So I can just say that, so output of an OR gate which drives the D input is nothing but X bar Q2 bar plus Q1 bar dot Q2 bar. So like this we have to find out the expression for D1, similarly the expression for D2, and similarly the expression for Z. So we know that all these expressions, both D1, D2 and Z, are in terms of Q1 bar, Q2 bar, and X bar. So only these terms will be there in the excitation equation for the D1, D2 and the output equation Z. So looking at this diagram, so now we will write the equations. D1 is equal to X bar Q2 bar. Similarly, Q1 bar Q2. Similarly, I'll write down for other two. Now output equation also similar method to be used for writing it. Okay. So now we have got excitation equations and output equations. So we can know that all these equations so uses the present state outputs and the inputs. Sometimes while in the examination or the requirement may come, so inputs will be given in the form of equation. We will be asked to write the diagrams from these equations. So we have to follow the reverse. So we have to draw the combination circuit with the flip-flop as per this equation. So sometimes the circuit will not be given, equations will be given. So we have to write the circuit with the help of these equations. So now we'll go to the step number 3. Now from the excitation equations and output equations, now we have to derive the transition equations. Derive transition equations. So what is the transition equations? Transition equations is nothing but the characteristic equations of the flip-flops. That means that we know that in the characteristic equations, we were writing the Q plus of the every flip-flop in terms of the present state, and also in this case it is an input also. So we have to write the Q plus, that is the next state outputs, in terms of the present state inputs and also the present inputs. So to derive the characteristic transition equations, we should be very clear what type of flip-flops we are used to design the circuit. In this case, we have assumed and also circuit is given with a D flip-flops. So we know that for D flip-flop, the characteristic equation is equal to Q plus is equal to D. So if we are taking a circuit where the JK flip-flops is used, so we should know that Q plus is in terms of JK inputs and the present state outputs Q and Q bar. So based on the flip-flop, we have to write the characteristic equation. Now, so let's write the now transition equation. So transition equation has to be written for every flip-flop. So for the flip-flop 1, we know that Q1 plus is equal to D1. Similarly, for the flip-flop 2, Q2 plus equals D2. Now let's substitute the value of D1 and the D2 from the previous step, that is from the excitation equations, into the transition equations. Now Q1 plus is equal to X bar Q2 bar plus Q1 bar into Q2. It is same. The excitation equation and transition equation may be the same in case of D flip-flop. So Q2 plus, it may be different for other flip-flops are used. Q1 bar, so Q2 X and the Q1 bar. So now we have got the transition equations for both the flip-flops. So transition equations are obtained by using the characteristic equation of the flip-flops and substituting the excitation equations in the characteristic equations. Now let's go to the step 4. So in the step 4, we have to prepare a transition table. So derive or write transition table. So transition table documents the transition and output equation in the form of columnar format. So transition table has got 3 columns. So the first column is called as present state. So present state, since 2 flip-flops are there, it is Q1, Q2. The second column of the transition table is nothing but next state. So next state is again represented by 2 variables, Q1 plus and Q2 plus. The next state do not depend only on the present state like in the counters. The next state depends on the present state and also the inputs, because input is also part of the transition equations. So that's why if input is a single variable, we have to write the next state for each of the value of the input variable. In this case, input is one variable, that is X. So I have to write down what will be the next state based on the present state for X is equal to 0. Similarly, what is the next state based on the present state when X is equal to 1. So 2 columns will be available under the next state. Similarly now, the third column is called as output. So output Z. So here also output Z depends upon the input value. So input X. If X is equal to 0, what will be the value? And X is equal to 1, what will be the value? Now, so all the present states possible, we will document the 0, 0, 0, 1, 1, 0, and the 1, 1. Now, so we have to write now for X is equal to 0, when the present state is 0, 0, what will be the next state? How we can find out? From the transition equations we can able to find out. For example, let's take one case. So q1, q2 both are 0, 0, X is equal to 0. So I want to find out q1 plus. So q1 plus is nothing but, so X is 0, so it will be 1. So in this case, so we can just see that X is equal to 0, it's a 1. So q2 is 0, it's a 1. So that it is, this term will be 1. So that I can write 1 here. Now similarly for the q2, so taking the values of q1, q2 and x0, 0, 0, 0, substituting this value in the q2 bar, in the q2 equation, so we get 0. So in the same fashion, so we have to find out when x is equal to 1, q1, q2, 0, 0, substitute in the equation and write down the values. So I got 0, 1 here. So similarly, output equation. Let's take the output equation. So output equation is this the equation. So q1 is 0, q2 is 0, and x is equal to 0. So in this case, so first case when x is equal to 0, 0 will get. In the case of x is equal to 1, so this term becomes 1, so that it will be 1. Same way, substituting the values for the next state, 0, 1 state, and using those equations, we'll get the following outputs. So it is 0 and this is 0. Similarly for the 1, 0, so we'll get 1, 0, and this is 0, 0, and this is 1, and this is 0. Similarly for the last one, if it 1, 1, it is 0, 0, it is 0, 0, and this is 1, and this is 0. Now, so this table is referred as a transition table, which documents the present state, next state, and the output. So the complete behavior of the given circuit, synchronous sequential circuit, is documented in this table. Now, the fifth step. So fifth step is convert the transition table into state table, that is generate state table. So what is a state table? State table is nothing but we are representing all the states which is in binary form, in the binary representation, using alphanumeric symbols. So here in the state tables, so let us assign A to alphanumeric symbol 0, 0, B to 0, 1, C to 1, 0, D to 1, 1. Now substitute in the earlier table, whatever the transition table, with these codes and complete the table. Now, so we know that, so it will be 0, 0 means it is a A, 0, 1 is a B, 1, 0 it is C, 1, 1 is a D. Now, so the next, this will be the present state. So this will be the next state with x is equal to 0 and x is equal to 1. So you know that the 1, 0 will be C state, and this will be B, 0, 1 is a B. Similarly, I can complete D, C, A, and this will be A and then A. So outputs will not change in the state table. Outputs will be same way. I'll copy the outputs. X is equal to 1. It's an output. So 0, 1 0 0 1 0 and this is 1 0. Now this table is called as a state table. Here all the states are represented by alphanumeric symbol. Now having represented this one, now we are left with the last step of the analysis of a synchronous sequential circuit. So this table, state table, clearly indicates given any state of the flip-flop, if the proper inputs are given, that is x is equal to 0 and 1, and the clock signal is applied to the circuit, it will just transition, it will take the transition from one state to another state. So representing these transitions in a pictorial format is called as a state diagram. So let's draw the state diagram. So when we writing the diagram, so we should have the table with us. So I have written this table here. Here I am demonstrating. So now when the same table, that is state table, is used to write the diagram here. Now for example, let's observe that. So how many states? There are 4 states there. So we have documented A, B, C, D. Now, so every state is by a node, and all the states takes the transition from one state to another state. So directed branches are used to indicate the transition from one state to another state. When you look at the branches, we have indicated 2 information on every branch. The first information is what is the input value when the transition happened. The second part of the data is what is an output during that state. So let's say we are now representing the first state transition. Assume that it is there in the A state now. Now the input applied now is equal to x is equal to 0. Now the transition is A to C. So now A to C is the one transition is shown by a directed branch. Now 0 indicates the x is 0, that is input is 0. So and the output is also 0. You can just see that here the output is also 0 when the x is equal to 0. So here a transition happens from one state to another state only with reference to clock cycle. Let's say it is remaining in the A state. When it is there in the A state, it has got an output which is nothing but 0. So that does not, when we indicate 0/0, that does not mean that output is available only during transition. Outputs are always available with that state. When it is there in the A state, it produces some output. That output depends upon the input. So since the output can be 0 or 1, or it can be 0 or it can be 1, so that depends upon the input. I cannot represent the output in the state itself, in the node itself. That's why we generally indicate the output on the branch side. So we will observe the one more. Now state A will move to state D. This is state B whenever x is equal to 1. So observe here. So now when the input is 1 and the clock signal is applied, then it moves from A to B. So when it is in the A, when x is equal to 1, the output is equal to 1. So always only one transition can bring a change in one state to another state. So let's observe one more. So now 1 0 is the C state. Now x is equal to 0. So C to C. So you can just see that in the C state, when the x is equal to 0 and the clock is applied, so it moves to the same state and the output when it is in the C state, when the x is equal to 0 is 1. So like this, looking at the state table, we can complete the state diagram. So this completes, so the sixth step in the analysis. So the sixth step in the analysis is, so writing the state diagram. So summarizing, any given sequential synchronous circuit can be analyzed with the help of 6 steps. Number one is we have to assign the state variables to all the flip-flop outputs, name all the inputs of the flip-flops with the excitation variables, then derive the excitation equations for all the inputs of the flip-flops and derive the output equation. These equations always is in terms of present inputs and also the present outputs. Then derive the transition equation which is based on the characteristic equation of the flip-flop. So with the help of transition equation, so we can write the transition table. Only with the help of transition equation we can write the transition table. Now the transition table can be represented by a state table and by the state diagram. So the last step in the analysis of any sequential circuit is the terminal behavior. So let's understand what is a terminal behavior. So now the circuit is given. The whole circuit can be understood by the state diagram. Now if the circuit is given an input sequence of 0, 0, 1, 0, 0, some sequence, if you assume the circuit is, to begin with, it is in a particular initial state, let's say A state. For this given sequence, what is the expected state sequence and what is the expected output sequence? Here, for every input or for every state to change, one clock cycle is required. So change from one state A to state C happen only during the clock cycle. So let's understand this with the help of the simulator. Now we'll assume that now it's in the A state. So I'll assume it is in the, this is the circuit diagram. So I will reset the simulator. So now Q1 is 0, Q2 is 0. That is in the A state. It will be the A state. Now, so look at this diagram. Now it is in the A state. The input what is applied is 0. The expected output is 0. Observe that. The input applied is 0. The expected output is 0. So that means that, so as per the state diagram, so it refers to the same thing. It is in the A, when the input is 0, the output is 0. Now, so now when it is in this state, now we will now give one clock pulse. So when we give a clock pulse, as per this state sequence, it has to, A should change to C. So we can see here, when it is in the A and input is 0 and the clock pulse is applied, it has to move to the C state. And during the transition and before the clock signal is applied, output is 0. So let's observe that. Now x is equal to 0. It is in the A state. I will give one clock pulse now. It has to move to the C state. Now it has, see that it has moved to the C state. So y 1 0 refers to the C state. Now, so now let's go to the next one. Now it's in the C state. I will apply the 0 input. So always the data input has to be applied before the clock pulse comes in any state. So now it is in the C state. We'll apply the 0 input. So when you apply the 0 input, expected output should be 1. So now it's in the C state. X is equal to 0. Output is 1. So you can just see that output is equal to 1. Input is 0. Now if I give another clock pulse now with x is equal to 0, it should move to the next state, that is nothing but C. Let's observe here now. It is in the now C state. You are giving an input 0. So already when you give an input, output is already 0. So it should move to the same state. In the sense, it should remain in the C state only. Now, so x is 0. It is in the C state. I'll give another clock pulse. It remain in the same C state. It will not change. You can just see that when x is equal to 0, it will remain in the same state. Now, So to change to another state now, we have to change the input. Now I'll apply the input is equal to 1. Whenever the apply input is equal to 1, output becomes 0. So I'll apply input is equal to 1. So output becomes, you can just see that it is 0. Now, after applying the input now, I give a clock pulse so that now it changes from C to A, it has to change. So when the X is equal to 1, I'll give a clock pulse, it should change to C to A. So now X is equal to 1, so I'll give a clock pulse, it will change to A is 0, 0. So like this, so we can analyze very easily, or we can write the output sequence and the change in the state sequence for the given input sequence using the state diagrams. So this is called terminal behavior. That means that given the circuit, we are predicting what is an expected output sequence for the given input sequence. So this is how the Mealy sequential network can be analyzed, and state diagrams and the terminal behavior can be documented.